Space is vast. It's almost impossibly big. Our current rockets are honestly pretty slow when you think about the distances involved. A trip to Mars, which is our nearest planetary neighbor, takes many months. And going to the next star system, Proxima Centauri, would take tens of thousands of years with our best technology today. That's a huge problem for humanity's dream of exploring the cosmos. We need something faster. We need a new kind of engine. We need a fuel source so powerful that it makes interstellar travel possible, not just a fantasy. This is where the idea of antimatter comes into the picture, a substance that holds the promise of unlocking the universe. Imagine a journey to another star, not in a lifetime, but in a matter of years. Imagine a spaceship that could accelerate to a significant fraction of the speed of light. This is the incredible possibility that antimatter rockets offer. The idea of antimatter has been a favorite in science fiction for a very long time. Writers and filmmakers love it because it just sounds so powerful and mysterious. Think of the Starship Enterprise from Star Trek. Its famous warp drive is powered by a matter-antimatter reaction. The ship's engines mix matter and antimatter to create the enormous energy needed to travel faster than light. In 1928, a young scientist named Paul Dirac was working on equations to describe the behavior of electrons. His mathematics produced a strange result. It predicted the existence of a particle that was just like an electron, but with an opposite positive charge. Just a few years later, in 1932, Dirac's strange prediction was proven to be true. A physicist named Carl Anderson was studying cosmic rays. He discovered a particle track in his experiments that matched Dirac's anti-electron perfectly. He named this new particle the positron. It was the first piece of antimatter ever detected. This was a monumental moment in physics. Physicists quickly realized what would happen if a particle and its antiparticle met. They would annihilate each other completely. So, what exactly is this mysterious substance we call antimatter? In simple terms, it's the mirror image of ordinary matter. Every particle of matter has a twin, an antiparticle. An electron has a negative charge, so its antiparticle, the positron, has a positive charge. When these antiparticles come together, they can form anti-atoms. An antiproton and a positron could orbit each other to create an atom of anti-hydrogen. This raises a fascinating and profound question for physicists. If matter and antimatter are perfect mirror images, why is our universe made almost entirely of matter? According to our best theories of the Big Bang, matter and antimatter should have been created in equal amounts at the dawn of time. If that were true, they should have all annihilated each other, leaving behind a universe filled with nothing but light. This process of annihilation is the most powerful and efficient energy source known to physics, and it is the secret behind the incredible potential of an antimatter rocket. It is harnessing the power of complete destruction for the purpose of creation and exploration. If the universe is missing its antimatter, where can we find it? Well, honestly, the answer is that we have to make it ourselves. These are particle accelerators, giant facilities like the Large Hadron Collider at CERN in Switzerland. The basic recipe for making antimatter is to smash particles together at incredibly high speeds. The process is incredibly difficult and requires an immense amount of energy, far more than you get back from the antimatter itself. The amount of antimatter we can produce this way is astonishingly small. After running these massive city-sized machines for an entire year, scientists at CERN can produce only about a nanogram of antiprotons. To make enough antimatter to fuel even a small probe to Mars, we would need to run our current facilities for many millions of years. Now we face the second colossal challenge. How do you store it? The only known way to do this is with a device called a penning trap. The antiparticles are held in a near-perfect vacuum, levitating in the middle of the trap, never making contact with the physical structure around them. The traps require continuous power to maintain the magnetic and electric fields. If the power fails for even a fraction of a second, the trap collapses, and the antimatter is lost in a burst of energy. So we have this incredibly powerful fuel. How do we turn that explosive energy into controlled thrust for a rocket? You need a supply of matter, usually hydrogen, and a separate, carefully contained supply of antimatter like antiprotons. You then bring these two together in a controlled way inside a reaction chamber. When they meet, they annihilate, creating a maelstrom of high-energy particles and gamma rays. The The solution that physicists and engineers propose is a magnetic nozzle. This is a cleverly designed system of powerful superconducting magnets that create a strong, specially shaped magnetic field. As these charged pions fly out from the reaction chamber, they're grabbed by the magnetic field. The field acts like an invisible funnel, gathering the particles and directing them into a focused beam. This beam of particles, moving at nearly the speed of light, is what provides the rocket's thrust. The annihilation process releases not only useful charged particles but also a flood of incredibly powerful gamma rays. The reaction chamber would need to be made of incredibly dense materials and surrounded by massive radiation shields. This shielding adds enormous weight to the spacecraft, which is a major challenge for any rocket design, as every kilogram requires more fuel to move. The design of an antimatter engine is therefore a delicate balancing act. These conflicting requirements make building a real antimatter rocket one of the most difficult engineering challenges imaginable. To truly appreciate the revolutionary potential of antimatter rockets, it's useful to compare them to other propulsion systems. Let's start with what we use today: chemical rockets. Next up are nuclear thermal and nuclear electric rockets. A nuclear thermal rocket uses a fission reactor to heat hydrogen to high temperatures, achieving a specific impulse of about 900 seconds. Nuclear electric propulsion, like an ion drive, uses electricity from a reactor to accelerate charged particles. These have a very high specific impulse, up to 10,000 seconds, but their thrust is incredibly low. This is where antimatter rockets enter a completely different league. A beamed core antimatter engine could have a specific impulse ranging from 10,000 to 100,000 seconds, but the pure annihilation rocket is the true champion. In theory, its specific impulse could be over 1 million seconds, or even higher. It could push a ship to 30% or even 50% of the speed of light. This is not just an incremental improvement, it's a fundamental game changer. The single greatest challenge standing between us and an antimatter rocket is production. We know how to make antimatter, but the process is, honestly, staggeringly inefficient. In fact, the energy needed to create a single antiproton is about 1 billion times more than the energy you get back when you annihilate it. All the antimatter ever created by humanity in all the particle accelerators around the world amounts to only a few nanograms. For a mission to Mars using a highly efficient engine, you would need milligrams of antimatter, which is millions of times more than we have ever produced. For an interstellar mission to Proxima Centauri, even with the most optimistic designs, you would need many grams, or perhaps even kilograms. This is, honestly, an astronomical quantity compared to our current capabilities. It is like trying to fill an ocean with a single eyedropper. We would need dedicated antimatter factories working around the clock. These facilities would be enormous, likely spanning several kilometers, and would consume a significant fraction of a country's entire power grid. Looking to the future, scientists are exploring new ideas for making antimatter more efficiently. Some have proposed using ultra-powerful lasers to create particle-antiparticle pairs from a vacuum. Others wonder if we might one day find natural sources of antimatter. Perhaps magnetic scoops could collect this sparse resource on long journeys through space. Beyond production and storage, there lies the terrifying issue of safety. An antimatter rocket is not just an engine, it is also the most powerful bomb that humanity could ever build. An accident during launch or in Earth's orbit would be a global catastrophe, releasing a wave of lethal radiation that could devastate the planet's biosphere. Handling the fuel would be an incredibly delicate operation. Every step, from manufacturing to loading it into the spaceship's storage traps, would need to be done remotely by robots. Perhaps the most chilling risk associated with antimatter technology has nothing to do with accidents, but with intent. The same physics that enables a Starship engine also provides the blueprint for the most destructive weapon theoretically possible. A terrorist group, or a rogue state that managed to steal even a tiny amount, a few milligrams, could threaten a major city with complete annihilation. The proliferation of this technology would be a global nightmare, creating a new and incredibly unstable arms race. Ultimately, the development of antimatter propulsion forces us to confront a profound question about human nature. Are we as a species mature enough to handle this kind of power? Before we can build the starships of our dreams, we would first need to build a global society based on unprecedented levels of trust, cooperation, and verification. The greatest barrier to the stars might not be in our physics or our engineering, but in ourselves. Science fiction has long been fascinated by the immense power of antimatter. In books and films, it's often treated as the ultimate power source, kind of like a magical key that unlocks the universe for humanity. The most famous example is, without a doubt, the Starship Enterprise from Star Trek. On the show, engineers in brightly colored uniforms casually monitor the flow of deuterium and anti-deuterium into a reaction chamber. In the movie Angels and Demons, a stolen canister of antimatter becomes a terrifying weapon, a ticking time bomb threatening Vatican City. While science fiction imagines starships effortlessly cruising the galaxy, the reality of antimatter research is far more grounded and methodical. Here, scientists aren't building warp drives. They're trying to answer fundamental questions about the universe by studying individual anti-atoms. The progress is measured not in light years traveled, but in the number of anti-hydrogen atoms they can create and hold, and the number of seconds they can keep them from annihilating. The gap between science fiction's vision and scientific reality is immense, but this really isn't a criticism of either. They simply serve different purposes. Science fiction is meant to inspire, to ask what if. The image of the Enterprise using its antimatter drive to explore strange new worlds has undoubtedly inspired countless young people to become scientists and engineers. Real-world science, on the other hand, is the slow, difficult process of building the boat to get to that distant shore. The potential benefits of mastering antimatter propulsion are almost as staggering as the challenges. If we could build a reliable antimatter rocket, it would fundamentally rewrite the rules of space exploration for humanity. With an antimatter-powered ship, a crewed mission to Jupiter's fascinating moons, like Europa with its hidden ocean, could be undertaken in months rather than a lifetime. The solar system would transform from a vast, almost insurmountable sea into a familiar neighborhood, with every world suddenly within our reach. Beyond our solar system lies the grandest prize of all, the stars. Antimatter propulsion is one of the very few technologies we can conceive of that makes interstellar travel a practical possibility. At such speeds, a journey to the nearest star system, Proxima Centauri, which is just over 4 light-years away, could be completed in under a decade. The very act of becoming an interstellar species would change humanity forever, broadening our perspective and perhaps ensuring our long-term survival. We stand at a crossroads, looking up at the vast starry expanse of the universe. In one hand, we hold the incredible promise of antimatter. The truth is that it is too early to know for sure. The science of antimatter is still in its infancy. We are like ancient mariners who have just discovered the principle of the sail, but have not yet learned how to build an ocean-going vessel. The dream of antimatter propulsion serves as a powerful beacon, guiding this long-term research and inspiring new generations to tackle these fundamental problems. If we are to see an antimatter rocket fly, the timeline will be measured not in years, but in decades and more likely centuries. A prototype storage device might be developed in the late 21st century, but a flight-ready system for an interstellar mission would be a product of the 22nd century or even later. The first robotic interstellar probe, powered by antimatter, might launch by the year 2250, with a human mission following a century after that. In the final analysis, the question of whether antimatter rockets become science or remain science fiction may depend less on the physics and more on us. If we can rise to the challenge, if we can build a world where such powerful knowledge can be managed safely and used for the benefit of all, then the dream of antimatter travel could one day become a reality. So the truth about antimatter rockets is that they are both science and science fiction. The science is real, grounded in the fundamental laws of our universe, but the starships themselves remain, for now, in the realm of fiction. Whether we ever embark on those incredible journeys to distant suns will be the ultimate test of our ingenuity, our perseverance, and, most importantly, our character. The stars are waiting, but the choice to reach for them is ours to make.